Least recently used page replacement algorithm presented by G. Satvika Reddy 22B01805540 and M. Jayasahiti 22B01805666 under the guidance of Dr. M. Prasad, PhD, Associate Professor, Department of CSE, SVCW Autonomous, Bhimavaram. Now, let us get into the topic. Our topic is memory management. So, memory management refers to the process of efficiently handling the computer's memory, making sure that all the programs and processes have the memory they need to run properly. It involves tasks like keeping track of which parts of memory are currently in use, allocating memory to programs which need it, and freeing up memory that is no longer required. For enhancing the memory management, page replacement algorithms are generally used. Need or place replacement algorithms. In computer systems, the main memory, which is the RAM, has limited capacity, while the demand for memory by various processes and applications often exceeds this physical limit. As a result, the operating system implements a technique known as virtual memory, where a portion of the hard disk is used as an extension of the physical memory. Page replacement algorithms are essential for memory management. So, the page replacement algorithms are generally used for managing the memory so that all process can utilize the memory efficiently. First algorithm is least recently used algorithm. The least recently used LRU page replacement algorithm is a type of algorithm used in memory management within the operating systems and the cache systems. It aims to manage the available memory efficiently by replacing the least recently used pages with newer pages or those that are more actively used. The basic concept behind the LRU algorithm is that the page or data that has not been accessed for the longest period of time is the least likely to be used in the near future. Therefore, when the system needs to replace a page in memory, it selects the page that has not been accessed for the longest time and replaces it with the new page. Coming to the implementation of the LRU algorithm. To implement the LRU algorithm, the system keeps track of the order in which the pages are accessed. This is often done using a data structure such as a linked list, a queue, or a stack, where the most recently accessed page is moved to the front, where the least recently accessed page is kept at the end. When a page needs to be replaced, the algorithm selects the page at the end of the list for the removal. The LRU algorithm is popular because it tends to perform well in situations where there is temporal locality, meaning that recently accessed pages are more likely to be accessed again in the near future, especially in the systems with large memory sizes. as it requires tracking the entire history of the page accesses. Now, let us look at some examples. Let's take the following reference string to understand the LRU page replacement algorithm in a better way. String is 5, 0, 1, 2, 0, 3, 2, 0, 3, 4, 1, 0, 5, 0, 4, 3, 2, 1, 2, 0, and 1. Now, find the number of page faults when the LRU page replacement policy is used. And also consider the page frame size to be 3. So, in the solution, let us take the reference string which is already given in the question. Now, let us look at the table where there are 3 frames and the string which is already given in the question, that is also the reference string, is taken at the top. And each of the string number is taken at a time at once at a time. So the total number of reference strings, that is equal to 21. Total number of page faults or page misses, that is equal to 14. We know that total number of page hits, which is page faults, is equal to total number of reference strings minus total number of page faults. Total number of page hits is equal to 21 minus 14, which is 7. Page fault probability is equal to total number of page faults divided by total number of reference strings. Page fault probability is equal to the total number of page faults, which is 14, divided by the total number of reference strings, that is 21. Hence, we get 0.67. Page fault percentage is equal to total number of page faults divided by total number of reference strings into 100. Page fault percentage is equal to total number of page faults, that is 14, divided by total number of reference strings, that is 21, into 100, that is equal to 67%. So the explanation for the above example is, firstly, there are 3 empty frames in the memory. Therefore, when 5, 0, and 1 come into the frame, they are allocated to the empty frame in order of their arrival. It occurs page fault because 5, 0, and 1 are not present in the memory. When 2 comes, it is not present in the memory. Therefore, the page fault occurs and it replaces the oldest page 5, which is the least recently used page. When 0 comes, it is present in the memory. Therefore, a page hit occurs and no replacement occurs. When 3 comes, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 1, which is the least recently used page. When 2, 0, and 3 comes, it is present in the memory. Therefore, a page hit occurs and no replacement also occurs. When 6, when 4 comes, it is not present in the memory. Therefore, page fault occurs and it replaces page 2, which is the least recently used page. When 1 occurs, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 0, which is the least recently used page. When 0 comes, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 3, which is the least recently used page. When 5 comes, it is not present in the memory. Therefore, page fault occurs and it replaces the oldest page, which is 4, which is least recently used page. When again 0 comes, it is already present in the memory. Therefore, a page hit occurs and no replacement occurs. When 4 comes, it is not present in the memory. Therefore, page fault occurs and it replaces the oldest page, which is 1, which is the least recently used page. When 3 comes, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 0, which is the least recently used page. When 2 comes, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 5, which is the least recently used page. When 1 comes, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 4, which is the least recently used page. When 2 comes, it is present in the memory. Therefore, page hit occurs and no replacement occurs. When 0 comes, it is not present in the memory. Therefore, a page fault occurs and it replaces the oldest page, which is 3, which is the least recently used page. When 1 comes, it is present in the memory already. Therefore, a page hit occurs and no replacement also occurs. Therefore, there is no replacement. Thank you.